Let's talk about the definition of exponentiation under these various conditions. And the remarkable thing is that, except with one notable exception, all of these things actually are equivalent. First off, the ordinary definition: z is a complex number and w is a positive integer, so something like 2 plus 2i to the fifth power. So that's what we're talking about for number one. The definition is exactly what you think it ought to be. So z to the w is going to be equal to z times z times z times z w times. The next one we'll talk about is what happens if I permit z to be any complex number other than 0, but w now can be any integer, not necessarily positive. So we're talking about something like 2 plus 2i to the 0, or else 2 plus 2i to the negative 5. Well, for positive numbers, we've already discussed it. If w is 0, then this is going to be defined to be equal to 1. And if w is negative, then we'll write this as 1 over z to the negative w if w is negative. And because, and the negative sign doesn't appear very well, and because w is negative, negative w is positive, and so that's defined by the first definition. Now I'm going to save the be careful one for last. Let's now consider the third one here. Z is greater than 0 and w is a rational number. So in other words, I have a positive base, something like 64, and I raise it to a rational number like 5/6. So the definition for this, if I have z to the p over q, the definition is that this is equal to the qth root of z, and I raise it to the pth power. Which begs the question, what is the qth root of z? The qth root of z if z is positive, the qth root of z is the unique positive solution to x to the qth power is equal to z. So that's what it means to be a qth root if the thing under the root is positive. More on that later when I get to the be careful case. Let's take number 4. Now suppose I don't have a rational base, but I have a real base. So number 4 would be something like 2 to the square root of 2. How do we define that? The way that this gets defined, if I have z to the w power, this would be defined as e to the w times the natural log of z, where the exponential function is defined to be the inverse of the log function, and the log function was defined to be the integral of 1 over x. So remarkably, this definition is equivalent to definition number 3. So number 3 and number 4, the one in brown and the one in green, look nothing like each other, but they actually do coincide. Let's now turn to definition number 5. The definition of a non-zero complex number raised to a rational power. So something like 2 plus 2y to the 5/6. Well, here's the definition. If we write z is equal to r times cosine theta plus I sine theta, then z to the w is equal to r to the w times cosine w theta plus I sine w theta. Remarkably, this matches definition number 1. By de Moivre's theorem, z to the n is equal to r to the n cosine n theta plus I sine n theta if n is an integer. So actually matches definitions 1 and 2. If I have a rational number, I just simply extend the to define it that way for rational numbers. So the expression here in gray was proven for integers using so definitions 1 and 2 match, and we'll simply extend that for rational numbers. Finally, number 6. And we'll come back to the one I skipped in a little bit. Number 6, z to the w, where w is a complex number now. So 2 plus 2i to the 1 minus I power, something that looks like that. In this case, z to the w is equal to e to the w times the logarithm of z. And one very important note that I forgot to write down over here. When I write r times cosine theta plus I sine theta, we need the restriction that the angle theta is between negative pi and plus pi. So we have to take that particular choice of theta. Now, the definition of logarithm for complex numbers goes like this: e to the w times the natural log of r plus I theta. And then typically the exponent must be simplified before the exponential function can be evaluated. Remarkably, definitions 5 and 6 are the same. If w is a rational number, then definitions 5 and 6 are both the same thing, and that is another review problem. Okay, now let's take a closer look at number 7, which I saved for last. The definition of a real number raised to the 1 over n power. The definition for 7 technically is the same thing as for 5. So if z is a real number, then it is certainly a complex number other than 0. If w is equal to 1 over n, then w is certainly rational. So the definition for 7, where I have something like a real number, whether it's 24 to the 1/2 or whether it's negative 24 to the 1/2. Other cases would be 27 to the 1/3 or else negative 27 to the 1/3. The definition for 7 matches the same thing that we have for 5. We have to express the number in trigonometric form and then use the definition that you see here in the grayish color. Now, what I want to emphasize is that the definitions that you see here may or may not be equivalent to square root of 24, square root of negative 24, cube root of 27, and the really crazy one, negative cube root of 27. Okay, now what are these things? Square root of 24, you know full well what that is. That's equal to 2 square root of 6. Okay, and these two match. So that matches what we would have here. Square root of negative 24, however, is undefined. There is no real number, so that the square root of negative 24 is, or so that x squared equals negative 24. That cannot be solved over the real numbers. So the square root of negative 24 technically is undefined. Negative 24 to the 1/2, that is defined. That's equal to 2i square root of 6. And this is kind of an ambiguity about the way that we teach secondary students. Like in the quadratic formula, we'll introduce students to the term square root of negative 24 when we really mean negative 24 to the 1/2 power. So that's a slight ambiguity. Now that's easy compared to what we're about to talk about. The cube root of 27 is equal to 3. And 27 to the 1/3 is also equal to 3, so those two match also. So for the positive case, the two definitions mean the same thing. This one's the weird one. Negative 27 cube root. So that means solve x cubed equals negative 27 over the real line and take the positive solution if there's any ambiguity. In this case, there's one real solution, x equals negative 3. Okay. However, if I come back to negative 27 to the 1/3, negative 27 to the 1/3, that is the 27 times cosine pi plus I sine pi to the 1/3. And so by the definition up here in the bluish color, that's equal to the cube root of 27, 3, times the cosine of pi over 3 plus I sine pi over 3, which is 3/2 plus I square root of 3 over 2. And clearly, these two things are not equal. Now, why does this happen? There are three complex numbers that when you cube them, you get negative 27. In this definition, I force the real solution. In this definition, I force the answer that has the least angle. The angle is the least. And if I have positive numbers, those two definitions match. If I have negative numbers and I have an odd denominator here, like 1/3, then they don't match. So the case of a negative base and something like 1 over an even number, that's kind of easy to understand. This one is a little bit trickier because the cube root of negative 27 must be a real number, but negative 27 to the 1/3 is a complex number, and it is the complex number, the complex solution, whose angle here is the least. So for the case number 7, the answer is in green here, and it does not match what you would typically think to be the answer, which has been written out here in gray. So anyway, those are the definitions of z to the w under the various conditions.